There is a number that astronomers use so casually, so routinely, that it has almost lost its ability to land with the weight it deserves. 100,000 light years. That is the diameter of the Milky Way, the galaxy you live in, the galaxy that contains the Sun, the galaxy whose faint smear of light you can see on a clear night, arching overhead from horizon to horizon. 100,000 light years. A light year is the distance light travels in 1 year, moving at 299,792 kilometers per second, the fastest speed anything in the universe can achieve. Light crosses the Atlantic Ocean in roughly 17 milliseconds. It circles the Earth 7 times per second. It reaches the Moon in 1.3 seconds and the Sun in 8 minutes. And a Milky Way is 100,000 of those years wide. If you fired a beam of light from one edge of our galaxy to the other, at the moment our species first learned to make stone tools, roughly 3.3 million years ago, that beam would not have arrived yet. It would still be travelling. It would not arrive for another 96.7 million years, and that is just the width. That is just crossing it in a straight line. Nobody said anything yet about the journey taking any longer than that, about any slower vehicle, about any human timescale. The moment you introduce a spacecraft, any spacecraft, including ones we can actually build, the numbers become so large that the word staggering fails entirely. You need new words, you need new frameworks. You need to rethink what travel means. If you enjoy videos that take the most extreme questions in space science and work through them honestly, that never round down the numbers to make them comfortable, but instead sit with the real figures and let them mean something, I genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The most common misconception about this topic is that it is a simple scaling problem. People hear that the fastest spacecraft humanity has ever launched, the Voyager probes, the Parker Solar Probe at its perihelion, travel at tens of kilometers per second, and they assume the answer to how long would it take to cross the Milky Way is just a matter of dividing the distance by the speed. That the question is fundamentally a word problem, the kind you might encounter in a high school physics class, and that the only interesting part is the size of the answer. This is wrong in a way that is worth unpacking carefully, because the real answer is far stranger and far more interesting than any simple arithmetic produces. The question of crossing the Milky Way is not just about speed and distance. It is about what speed means at the edge of its physical limit, about what time means when you are moving close to the speed of light, and about the engineering constraints of propulsion that make interstellar travel the hardest problem our civilization has ever faced, about the structure of the galaxy itself and why crossing it is not like crossing an ocean, but something qualitatively different. The answer depends on who is measuring the time, on what physics you are willing to assume, and on whether you are asking about what the travelers experience or what the people they left behind experience. The answer is not one number. It is a family of numbers, and each one reveals something different about the universe. Begin with the galaxy itself and what it actually means to cross it. The Milky Way is a barred spiral galaxy, a rotating disk of stars, gas and dust, with a central bar-shaped structure from which 2 major spiral arms emerge. Surrounded by a diffuse halo of older stars and dark matter extending far beyond the visible disk. Its diameter, measured across the stellar disk, is approximately 100,000 light-years. But this number, while standard and useful, already conceals some complexity. The Milky Way is not a uniform disk. It is thicker at the centre and thinner at the edges. The central bulge, the dense, roughly spherical concentration of older stars surrounding the galactic core, has a diameter of perhaps 10,000 light-years and a thickness of around 6,000 light-years. The disk itself, where the Sun lives and where most of the galaxy's star formation occurs, is roughly 1,000 light-years thick at our location, some 26,000 light-years from the galactic centre. The halo of older stars and globular clusters extends 100,000 light-years or more above and below the disk plane. The dark matter halo, the invisible scaffolding of mass that holds the galaxy together gravitationally, and whose nature remains one of the deepest unsolved problems in physics, extends for perhaps 300,000 to 600,000 light-years in all directions, encompassing not just our galaxy, but reaching toward the Andromeda galaxy, our nearest large neighbour. But these numbers, while accurate, do not yet convey the lived texture of the galaxy's structure, and understanding that texture matters for appreciating what a crossing actually means. The Milky Way is not a smooth disk. It is a turbulent, dynamic, structured environment, shaped by the interplay of gravity, stellar winds, supernova, explosions, magnetic fields, and the slow orbital dance of hundreds of billions of stars around a common centre. Let us walk through those structures, layer by layer. The spiral arms themselves are not solid objects. They are density waves, regions of slightly higher stellar and gas density that persist even as individual stars pass through them. The way a traffic jam persists on a highway, even as individual cars flow through it and emerge on the other side. The enhanced density in a spiral arm triggers star formation. The gas clouds in the arm are compressed by the density wave until they collapse under their own gravity, igniting new stars. The young, hot, massive blue stars that form in this way are extraordinarily luminous and short-lived, burning bright for a few million years before exploding as supernovae, which is why the spiral arms are most visible in the blue and ultraviolet light of young, massive stars. But these stars are simply the tracers of the arms, not the arms themselves. The bulk of the stars in the Milky Way, older, cooler, less luminous red and orange stars, are distributed more uniformly through the disk, not concentrated in the arms. The Milky Way has two major arms, the Perseus arm and the Scutum Centaurus arm, and several minor arms and spurs. Our Sun sits in one of these spurs, called the Orion Arm or Local Spur, a relatively minor feature roughly 10,000 light-years long and a few hundred light-years wide. The Orion Arm connects the Perseus Arm to the Sagittarius Arm, and it is home to a number of famous star-forming regions visible to the naked eye, the Orion Nebula, where new stars are forming right now, roughly 1,300 light-years away. The Carina Nebula, one of the largest star-forming regions in the galaxy, about 7,500 light-years away, and the Pleiades, a young open cluster of stars formed from a common molecular cloud, about 440 light-years away. Between the spiral arms are the inter-arm regions, quieter structures of the galaxy where the stellar density is lower and star formation is less active. The interstellar medium in these regions is thinner, the molecular clouds sparser, the young blue stars absent. A traveller crossing the galaxy would pass through alternating zones of richness and relative emptiness. The dense, active spiral arms with their star-forming nebulae and hot young stars, and the quieter inter-arm regions where the galaxy's older stellar population goes about its business without the drama of ongoing star birth and stellar death. The older stars in the Milky Way reside in the galactic bulge and in the globular clusters, scattered through the halo. Globular clusters are spherical collections of between 10,000 and several million ancient stars, gravitationally bound and orbiting the galactic center in roughly spherical orbits, rather than the disk orbits of disk stars. They're among the oldest structures in the universe. Many have ages of 12 to 13 billion years, meaning they formed in the first billion years after the Big Bang, when the universe was still a young and fiercely active place. There are roughly 150 known globular clusters associated with the Milky Way, and they range from the spectacular Omega Centauri, the largest known, containing roughly 10 million stars packed into a sphere about 150 light-years across, visible as a fuzzy fourth magnitude patch of light in the seventh sky, to small, sparse clusters barely distinguishable from random stellar associations. A traveller crossing the galactic halo might pass through or near several of these ancient cities of stars, each one a time capsule from the early universe. The galactic centre itself deserves its own description, because it is one of the most extreme environments in the Milky Way and the focal point of a galaxy's gravitational structure. Like South Sagittarius A, the supermassive black hole at the centre was first identified in 1974 by Bruce Ballack and Robert Brown as a compact radio source in the direction of Sagittarius, and its nature as a black hole was firmly established over the following decades through the observation of stellar orbits by teams led by Reinhard Genzel at the Max Planck Institute and Andrea Ghez at UCLA, work for which they shared the 2020 Nobel Prize in Physics. The stars orbiting Sagittarius A star within a fraction of a light year of the black hole move at thousands of kilometers per second. 7.2, the best monotrated of these stars, completes one orbit in about 16 years and reaches a peak speed of about 7,650 kilometers per second at closest approach, fast enough that general relativistic corrections to its orbit are significant and detectable. The precession of S2's orbit, measured over multiple complete orbits, confirms the predictions of general relativity in the strong field regime at the galactic center. Surrounding Sagittarius A star, within a few light years, is the nuclear star cluster, one of the densest stellar environments known, containing tens of millions of stars in a region only a few light years across. The density of stars in this region exceeds the density in any globular cluster by factors of hundreds. The night sky from a planet in the nuclear star cluster, if such planets exist and are habitable, which is unlikely given the intense radiation and tidal forces, would contain millions of stars as bright as the full moon is from Earth. The sky would never be dark. Beyond the nuclear star cluster, within a few hundred light years of center, is the central molecular zone, a dense ring of molecular gas, the raw material of star formation, surrounding the galactic center. Within this zone, star formation occurs at a rate per unit area many times higher than in the rest of the galaxy. Massive young stars are born here in dense clusters, live their brief brilliant lives, and die in supernovae that inject energy into the surrounding medium, driving turbulence and influencing the future rate of star formation. The Arches cluster and the Quintuplet cluster, both within a few hundred light years of Sagittarius AD, are among the most massive and luminous young star clusters known in the galaxy, containing hundreds of massive stars whose combined luminosity is millions of times that of the Sun. The image of the Milky Way's central black hole, The shadow of Sagittarius A dot, surrounded by a ring of hot, glowing gas, was captured for the first time in 2022 by the Event Horizon Telescope, a global network of radio observatories acting together as a single Earth-sized interferometer. The image shows a roughly circular shadow, about 50 microarcsecs in angular size, equivalent to imaging a grain of sand on the surface of a moon from Earth, consistent with the predictions of general relativity for a black hole of 4.15 million solar masses. The photon ring surrounding the shadow is the bent light of the accretion disk, circling so close to the event horizon that some photons orbit the black hole multiple times before escaping. The image is a triumph of observational astronomy, and it is also a reminder of what sits at the center of our galactic home, an object so massive and so complex that not even light escapes from its surface, around which the entire Milky Way revolves on timescales of hundreds of millions of years. So when we ask how long it would take to travel across the Milky Way, we are asking how long it would take to traverse all of this: the local spur, the spiral arms, the interon regions, the inner disk where stars grow denser and younger, the central molecular zone, the nucleus star cluster, the neighborhood of Sagittarius A back, and then back out through the far side of the bulge, through the far spiral arms, through the outer disk where stars grow sparse and metal poor, to the edge of the stellar disk, 100,000 light years of the most complex and varied gravitational and electromagnetic environment in our portion of the universe. So when we ask how long it would take to cross the Milky Way, we need to ask which part. Across the stellar disk, the most conventional answer, the journey is 100,000 light years. Across the full dark matter halo, it is 3 to 6 times longer. Crossing from the edge of the stellar disk on one side to the edge on the other, passing through the galactic center, through the bar, through the spiral arms, through regions of star-forming nebulae and ancient globular clusters and dense stellar nurseries and vast empty voids between the arms. This is the journey we will be describing. 100,000 light years. Remember that number. Everything that follows is an attempt to make it real. The Sun is located roughly 26,000 light years from the galactic center, in a relatively quiet region between two major spiral arms, the Perseus arm and the Sagittarius arm, in a minor feature sometimes called the Orion arm or local spur. We are not in a particularly special place. We are not near the center, where stellar density is many times higher, and the supermassive black hole Sagittarius A' holds court with a mass 4 million times that of the Sun, distorting the orbits of nearby stars in ways we can observe directly. We are not in the outer reaches of the disk, where stars are sparse, metal poor, and planets are less likely to contain the chemical complexity that life on Earth acquires. We are in a middle suburb of a spiral galaxy, orbiting the center at roughly 220 kilometers per second, completing one full orbit, one galactic year, in approximately 225 to 250 million years. The last time the Sun was at its current position in its orbit, the dominant land animals on Earth were early dinosaurs. The time before that, the first vertebrates were just learning to breathe air on land. Now, the journey. How long does it take to cross this structure? Let us begin at the bottom of the ladder, with the technology we have actually built, the spacecraft we have actually launched, and the utterly humbling arithmetic that results. The fastest human-made object ever to leave Earth on a sustained trajectory is a matter of some definitional nuance. Voyager 1, launched in September 1977, and now the most distant human-made object from Earth, at roughly 23 billion kilometers, travels at approximately 17 kilometers per second relative to the Sun. This is fast by any human standard. It crosses the distance between New York and Los Angeles in roughly 4 minutes. It covers the Earth-Moon distance in 6 hours, but it covers 1 light year in approximately 17,500 years. 1 light year. The width of the Milky Way is 100,000 light years. At Voyager 1 speed, crossing the Milky Way would take approximately 1.75 billion years, 1,750,000,000 years. For reference, 1.75 billion years ago, the most complex life form on Earth was a single-celled organism. The first multicellular life would not appear for another 300 million years. The first animals would not appear for another billion years. The dinosaurs would not appear for another 1.5 billion years. Voyager 1, at its current speed, would take longer to cross the Milky Way than it took complex life to evolve from single cells on Earth. The Parker Solar Probe, NASA's sun-grazing spacecraft that was launched in 2018 and reaches speeds of up to 692 kilometers per second at its closest approach to the Sun, making it the fastest human-made object ever. At those moments, would do better. At 692 kilometers per second, crossing the Milky Way would take approximately 43 million years, still longer than the existence of the genus Homo, still roughly 3 times longer than the dinosaurs existed. Still so long that the galaxy itself would have rotated roughly a fifth of a turn during the journey, meaning the destination you started toward would not be where you aimed when you arrive. The New Horizons spacecraft, which flew past Pluto in 2015 and is now heading out of the solar system at roughly 14 kilometers per second, would take approximately 2.1 billion years to cross the Milky Way. The various probe concepts that have been seriously proposed for interstellar travel, including the Breakthrough Starshot Initiative, which proposes using powerful ground-based lasers to accelerate gram-scale light sails to 20% of the speed of light, represent the current frontier of serious engineering thinking. At 20% of the speed of light, 60,000 kilometers per second, the Milky Way crossing would take 500,000 years. 500,000 years. Modern Homo sapiens has existed for only 300,000 years. A Breakthrough Starshot probe, if it could be sustained in steered, and if it actually reached its target speed, would take longer to cross the galaxy than our species has been anatomically modern. Each of these numbers illustrates something important. The gulf between any speed accessible to current or near-future human technology and the speed needed to make interstellar, let alone intergalactic, travel a human timescale endeavor. There is no gradual scaling available. You do not make this journey practical by building a better rocket. You do not get there by improving chemical propulsion by a factor of 10 or even a factor of 1,000. The problem is categorical, not incremental. You are fighting against a distance measured in units of light travel time, and the only vehicle that trivially crosses such distances is light itself. Everything slower than light is slower than the unit of measurement, and light itself, the fastest thing in the universe, takes 100,000 years. So let us talk about what happens as you approach the speed of light. Because this is where the physics becomes genuinely extraordinary, and where the answer to our question fractures into 2 very different answers depending on who you are asking. Special relativity, Einstein's theory of space and time, published in 1905, tested to extraordinary precision in particle accelerators, and GPS satellites and muon detectors and every other precision physics experiment for over a century tells us something remarkable about motion at high velocities. Time is not absolute. Simultaneity is not universal. The rate at which time passes depends on how fast you are moving relative to other observers. This is not a philosophical claim about the perception of time. It is a physical fact about the structure of space-time. Moving clocks run slow. Not appear to run slow, actually run slow, in a way that has real, measurable, irreversible consequences. The mathematical expression of this is the Lorentz factor, denoted by the Greek letter gamma. Gamma is a number that depends on your velocity, defined as gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At low velocities, at the speeds of cars or aircraft or even the Voyager probes, gamma is so close to 1 that the time dilation is undetectable. A Voyager probe, travelling at 17 kilometers per second, has a gamma factor of 1.616. The time dilation it experiences is 16 parts in a billion, completely negligible, unmeasurable, without atomic clocks of extraordinary precision. But as the velocity approaches the speed of light, the denominator of the gamma expression approaches 0 and gamma approaches infinity. At 99% of the speed of light, gamma is approximately 7.1. At 99.1.9% of the speed of light, gamma is approximately 22.4. At 99.99%, gamma is approximately 77.7% of the speed of light. At 99.99% of the speed of light, gamma is approximately 700. What does a gamma factor of 707 mean in practice? It means that for every year of time that passes on a ship travelling at 99.9999% of the speed of light, 707 years pass for observers who remain stationary. The travellers age 1 year. Their families age 707 years. The universe ages 707 years. And in 707 years, at 99.9999% of the speed of light, the ship travels 707 light years. From the ship's reference frame, the journey feels like it took 1 year. From the galaxy's reference frame, the journey took 707 years. This is the key to what we are about to discuss. If you are asking how long it takes to cross the Milky Way, from the perspective of the travellers, the people on the ship, experiencing the journey, aging through it, then the answer depends only on the gamma factor you can achieve. If you can achieve gamma of 100,000, the travellers experience the Milky Way crossing in 1 year, even though 100,000 years pass for the rest of the universe. If you can achieve gamma of 1,000, the crossing takes 100 years from the traveller's perspective, while 100 million years pass outside. The traveller's time and the universe's time are completely different quantities, and asking, how long does it take to cross the Milky Way? Without specifying which frame of reference you mean, it's like asking how far is New York from London? Without specifying whether you mean the straight line distance through the Earth, or the great circle distance along the surface, the question is well posed only once you specify the reference frame. Let us now build the ladder of possible journeys, from the realistic to the physically extreme, calibrating each one with both the ship time and the external time, and understanding what each level of technology implies. At the first rung, chemical propulsion, the technology we have actually mastered. The specific impulse, a measure of how efficiently a rocket uses its propellant, of the best chemical rockets ever built, the Saturn V or the Space Shuttle mean engines, produces exhaust velocities of around 4 kilometers per second. The maximum velocity achievable by a rocket depends on the ratio of the initial mass mostly propellant, to the final mass, the payload. The Tsiolkovsky rocket equation, the fundamental governing equation of rocketry, tells you that to accelerate a payload to velocity v, you need a mass ratio of e to the exhaust velocity, and e is Euler's number, approximately 2.718. To accelerate a payload to 40 kilometers per second, roughly twice the escape velocity from the solar system, using chemical propulsion with a 4 kilometer per second exhaust velocity, you need a mass ratio of e to the power of 10, approximately 22,000. For every kilogram of payload, you need 22,000 kilograms of propellant. To reach 100 kilometers per second, still a tiny fraction of the speed of light, the mass ratio becomes e to the power of 25,000, approximately 72 billion. For every kilogram of payload, 72 billion kilograms of propellant. A human crew capsule weighing a few tons would require propellant measured in the mass of small moons. Chemical propulsion for interstellar travel is not merely impractical, it is physically impossible at any scale of engineering that can reasonably be imagined. The rocket equation is merciless. This is why every serious proposal for interstellar travel abandons chemical propulsion and looks elsewhere. The next rung of the ladder is nuclear propulsion, and it represents the first technology within the plausible reach of engineering that can actually change the numbers meaningfully. Nuclear propulsion comes in two main variants: nuclear thermal, in which a nuclear reactor heats propellant to very high temperatures before expelling it, achieving exhaust velocities of around 8 to 10 kilometers per second, roughly twice the best chemical rockets; and nuclear pulse propulsion, in which a series of nuclear explosions behind the spacecraft push it forward, potentially achieving exhaust velocities of thousands of kilometers per second. The nuclear pulse concept was seriously studied in the late 1950s and 1960s under the name Project Orion, funded by the US Department of Defense and staffed by some of the most creative physicists of the era, including Freeman Dyson. Orion used small nuclear bombs, hundreds or thousands of them, exploding behind a large pusher plate, with shock absorbers between the plate and the spacecraft to cushion the impulse. The concept was physically sound. It was not, ultimately, the rocket equation that killed it. Nuclear pulse propulsion has a sufficiently high exhaust velocity that mass ratios become manageable, but rather the 1963 Partial Nuclear Test Ban Treaty, which prohibited nuclear weapons detonations in space and in the atmosphere. Orion was a program that the physics permitted and politics stopped. Freeman Dyson calculated that an Orion-type spacecraft, scaled up to a size that could carry a crew and the necessary nuclear bombs, could potentially reach speeds of around 1% of the speed of light. At 1% of the speed of light, crossing the Milky Way takes 10 million years. The time dilation at 1% of the speed of light is negligible, a gamma factor of essentially 1, meaning ship time and external time are virtually identical. This is still a geological timescale. It is not a human solution to the problem of crossing the galaxy, but it is a 500-fold improvement over chemical rockets, and it is technology that we understood how to build in the 1960s, constrained only by political will and the shortage of compact nuclear weapons. The next rung is fusion propulsion. Nuclear fusion, the process that powers the sun, in which light atomic nuclei are fused together to release energy, converting a fraction of their mass directly into energy via E equals mc squared, is far more energetically efficient than fission. Fusion of deuterium and helium-3 releases approximately 339 megajoules per gram of fuel, compared to roughly 1 megajoule per gram for the best chemical fuels. The exhaust velocities achievable with fusion propulsion depend on the specific reaction and the efficiency of conversion, but they could in principle approach several percent of the speed of light. The British Interplanetary Society's Project Daedalus, conducted in the 1970s as a serious engineering study of an uncrewed interstellar probe, proposed a two-stage fusion rocket powered by inertial confinement fusion of deuterium and helium-3 pellets. The design calculated a final velocity of about 12% of the speed of light, enough to reach Barnard's star, the nearest solar-type star, at 5.9 light-years in about 50 years of ship time. At 12% of the speed of light, crossing the 100,000 light-year Milky Way takes approximately 833,000 years of ship time, a gam factor still essentially equal to 1 at this speed, so external and ship time are virtually identical. Project Daedalus required approximately 50,000 tons of helium-3 as fuel, an element that is vanishingly rare on Earth but relatively abundant in the atmospheres of the outer planets, particularly Uranus and Neptune. The mining and transport of this helium-3 from the outer solar system would be an enterprise of civilization-scale effort. Daedalus was not proposed as imminent technology. It was proposed as a demonstration that fusion propulsion, while requiring enormous resources, is within the reach of the laws of physics, rather than requiring any violation of them. The conceptual descendant of Daedalus is the Icarus Interstellar Project and various academic proposals for fusion-propelled interstellar craft. The numbers are always similar in character: exhaust velocities of a few to 10% of the speed of light, final velocities of a fraction of that due to the mass ratio constraints, journey times to the nearest stars of centuries to millennia, and Milky Way crossing times of millions of years. Fusion propulsion is vastly better than mechanical or nuclear fission, and it makes the nearest stars accessible on timescales comparable to human civilization's history. But it does not make the galaxy accessible, not on any timescale a continuous civilization could sustain. This is where the proposals begin to become speculative in interesting and productive ways. The next major category of propulsion concept is beam-powered propulsion, schemes in which the spacecraft does not carry its own energy source, but instead receives energy from a powerful beam projected from the launch site. The most technically developed of these is the laser sail concept, championed in recent years by the Breakthrough Starshot project, founded by Yuri Milner in 2016. The concept is straightforward in principle. A gram-scale sail, made of highly reflective material a few meters across, is accelerated by a ground-based array of lasers delivering roughly 100 gigawatts of power focused on the sail. The radiation pressure of the laser beam pushes the sail, which must be extremely thin and extremely reflective to survive the intensity without burning. Calculations suggest that such a system could accelerate the sail to around 20% of the speed of light in a matter of minutes. At 20% of the speed of light, the Milky Way crossing takes 500,000 years in ship time. Still nearly negligible time dilation at this velocity. The engineering challenges are formidable. The laser array would be the most powerful coherent light source ever built by many orders of magnitude. The sail material does not currently exist. Steering and communication with a gram-scale probe at a fifth of the speed of light present enormous difficulties, and deceleration at the destination is not addressed in the basic concept. But the physics is sound. No new science is required, only new engineering. Beam propulsion can in principle reach higher speeds than any rocket, because it is the rocket's equation, the spacecraft carries no propellant. The limitation is instead the engineering of the beam and the sail, and the distance over which the beam can be focused. A laser array powerful enough to accelerate a sail to 20% of the speed of light over a distance of a few million kilometers would, beyond that distance, begin to diffract. The beam would spread, and the intensity on the sail would drop. To reach higher velocities, you need a larger aperture laser array, or you accept that you can only accelerate over a limited distance. Antimatter propulsion is the next rung on the conceptual ladder, and it is important to discuss it carefully, because it is simultaneously the most energy-dense propulsion concept physically possible and the most hopelessly impractical. When matter and antimatter meet, they annihilate completely. All of their mass is converted to energy via E = mc squared, with 100% efficiency. This is not the partial conversion of fission, which converts about 0.1% of mass to energy, or fusion, which converts about 0.7%. It is total conversion. The energy density of matter-antimatter annihilation is approximately 9 times 10 joules per kilogram, about 10 billion times the energy density of chemical fuel, and about 140 times the energy density of fusion. Antimatter-matter rocket, using this reaction to produce thrust, could, in principle, achieve exhaust velocities approaching the speed of light, making the rocket equation manageable even for relativistic journeys. The gamma factors needed to make the Milky Way crossing a human lifetime journey, gamma of around 100,000, would require accelerating to 99.9,995% of the speed of light, which is energetically demanding, but not physically impossible with antimatter fuel. The problem is not the physics of the engine, the problem is the fuel. The entire production of antimatter by human civilization, by all the particle accelerators ever built, over all the decades they have operated, amounts to perhaps a few nanograms total. A nanogram, 1/1000th of a gram. The energy to produce a kilogram of antihydrogen using current methods would be roughly 10 million times the current annual energy output of human civilization. Antimatter is not a fuel source. It is a theoretical fuel source for an imagined future civilization with energy resources thousands of times beyond our own. Thinking about antimatter propulsion is a useful way to understand the physics of what is possible in principle. It is not a roadmap to a spacecraft. But there is one proposal for interstellar propulsion that occupies a unique position in the hierarchy. It is physically possible, requires no exotic matter or antimatter, uses a fuel source available throughout interstellar space, and was worked out in mathematical detail by a physicist named Robert Bussard in 1960. It is called the Bussard ramjet. The interstellar medium, the gas and dust that fills the spaces between stars, is not empty. It contains, on average, about 1 hydrogen atom per cubic centimetre. This is an extraordinary low density by any earthly standard, far lower than the best vacuum achievable in any laboratory. But the Milky Way is vast, and a spacecraft travelling through it sweeps through a very large volume per second. Bussard proposed a spacecraft with a large electromagnetic scoop extending perhaps thousands of kilometres in diameter that would collect the hydrogen atoms from the interstellar medium as it travelled, funnel them into a fusion reactor at the centre of the spacecraft, and use the fusion reaction to produce thrust. The scoop collects fuel from the interstellar medium, the fuel is fused, the products are expelled to produce thrust. No propellant needs to be carried, no propellant runs out. The ship is, in principle, self-fueling at any speed, for any distance, anywhere in the galaxy where there is interstellar hydrogen. The Bussard ramjet captured the scientific imagination immediately. It appeared in numerous science fiction stories, most famously Paul Anderson's Tau Zero in 1970, in which a ramjet, unable to decelerate, accelerates indefinitely through the universe, the time dilation growing ever more extreme. The physics is intoxicating. A ship that can travel indefinitely, accelerating continuously, with ship time compressing relative to external time as the gamma factor climbs. In principle, with continuous acceleration at 1 grams, the same acceleration you feel sitting in your chair on Earth, comfortable, sustainable, no crashing G-forces, how long does it take to cross the Milky Way in ship time? The answer is deeply counterintuitive. At a constant acceleration of 1 grams, the ship reaches 50% of the speed of light in about a year. It reaches 99% in about 2 years. It reaches 99.9% in about 3 years. The gamma factor climbs exponentially, and the ship time required to cross 100,000 light years at 1 grams of continuous acceleration is approximately 12 years. 12 years. The ship time for a Milky Way crossing under continuous 1 gram acceleration is roughly the time from a child's birth to the start of middle school. The external time elapsed is, of course, 100,000 years, but for the travellers, the journey's a human-scale adventure, not a civilization-requiring project, just a long journey. But the Bussard ramjet faces serious physical obstacles. The first is that the fusion of proton-proton hydrogen, the reaction that would be available in the interstellar medium, is not the same as the easier deuterium-deuterium or deuterium-helium-3 reactions that fusion research focuses on. Proton-proton fusion is the reaction that powers the Sun, but it proceeds so slowly that it cannot be reproduced in the reactor at any practical scale. The Sun gets away with it because its core contains a number of hydrogen atoms so enormous that even an incredibly slow reaction rate produces enormous total power. A ramjet reactor cannot contain anything like the Sun's number of atoms, and proton-proton fusion at reactor scales is essentially non-existent. This problem has been known for decades and has not been resolved. The second problem was identified in the 1970s by researchers who pointed out that the interstellar hydrogen collected by the scoop is not just fuel, it is also a drag source. The magnetic scoop interacts with the interstellar medium in ways that create electromagnetic drag, and detailed calculations suggest that the drag may exceed the thrust from fusion, making the net result deceleration rather than acceleration. The Bussard ramjet may push you backward. Modified versions, the catalytic ramjet, the ramjet combined with onboard fuel, the laser-boosted ramjet, have been proposed to address these issues. None have achieved the elegant self-sufficiency of the original concept. The ramjet remains one of the most physically beautiful ideas in interstellar propulsion, and one of the most frustrating, because it offers so much in principle and delivers so little in practice. There is one more category of propulsion concept that needs to be addressed, not because it is remotely practical or even clearly possible within our current understanding of physics, but because it changes the nature of the question entirely. It is the Alcubierre warp drive, proposed by the Mexican physicist Miguel Alcubierre in 1994, and it represents the only known concept that would allow faster-than-light travel, or its practical equivalent, without violating the letter of special relativity. Alcubierre's insight was that special relativity prohibits objects from moving through space faster than light. It says nothing about space itself moving. The expansion of the universe is, in a sense, space moving. Distant galaxies recede from us at speeds exceeding light because the space between us is expanding, not because they are moving through space at that speed. Alcubierre proposed that you could, in principle, construct a bubble of space-time around a spacecraft, in which the space in front of the bubble contracts and the space behind it expands. The spacecraft inside the bubble is stationary with respect to the space immediately around it. It feels no acceleration, no tidal forces, no violation of special relativity locally. But the bubble itself moves through the larger space-time at any speed, because it is the space-time that is moving, not the spacecraft within it. The mathematics work out The spacetime metric Alcubierre proposed as a valid solution to the equations of general relativity, in the same sense that the Schwarzschild metric for black holes is a valid solution. The problem is the engineering. To maintain the warp bubble, you need a region of spacetime with negative energy density, a region in which the energy of empty space is less than zero. Negative energy density is possible in principle in quantum mechanics. The Casimir effect produces regions of negative energy density between closely spaced metal plates, but the amount of negative energy needed to maintain an Alcubierre warp bubble of spacecraft size, calculated using general relativity, is on the order of the mass energy of a planet like Jupiter with a negative sign. You need Jupiter's mass worth of negative energy concentrated in the bubble wall. No known mechanism can produce negative energy at anything remotely approaching this scale, and there are serious theoretical reasons to doubt that arbitrary amounts of negative energy can be produced by any quantum mechanical process. Subsequent work by Harold White at NASA and others has suggested that the required negative energy might be reduced by modifying the shape of the warp bubble, using a thinner, oscillating bubble rather than a uniform spherical one, potentially reducing the required negative energy to more manageable amounts. The research continues in the theoretical physics sense, but no experimental demonstration of warp field physics has been achieved, and the concept remains firmly in the domain of speculative physics rather than engineering. Why discuss it at all? Because the Alcubierre drive, if it worked, would allow crossing the Milky Way in effectively zero ship time at any desired speed, with no time dilation for the passengers and no time elapsed externally except the light travel time divided by the warp factor. It is the ultimate answer to the question, how long does it take to cross the Milky Way? If warp drives are possible, the answer is, as long as you want. If they are not, and the preponderance of current evidence suggests they are not, or at least not with any plausible energy budget, then the question returns to the relativistic framework we have been building. Maximum speed, the speed of light. Minimum ship time, 12 years at 1 grams of continuous acceleration. External time, always at least 100,000 years, no matter what. Let us now sit with the relativistic case more carefully, because it is the physically achievable extreme, and because the numbers that emerge from it are worth understanding in full detail. Imagine a spacecraft that can sustain constant acceleration of 1 standard grams, 9.8 meters per second squared, identical to the gravitational pull you feel on Earth's surface. This is a deliberate choice. 1 grams provides comfortable conditions for a human crew. They feel their normal weight. Their muscles do not atrophy. Their cardiovascular systems are not stressed by weightlessness. It is the most humane acceleration for a long journey. And it is also, conveniently, an acceleration that gives the most intuitive relationship between ship time and the gamma factor. Because at 1 grams of continuous acceleration in space, you pass physical milestones at very human-relevant times. As the ship accelerates, the relationship between the proper time of the travelers, the time they experience, measured by their clocks, experienced in their bodies, and the coordinate time of an external observer, is given by the relativistic rocket equations, which are more complex than the simple gamma factor relationship, but reduced to it at high velocities. Under constant 1g acceleration, the ship reaches the following speeds at the following ship times: 10% of light speed in roughly 35 days, 50% in about 200 days, 86% in about 1 year, 99% in about 2.1 years, 99.9% in about 3.1 years, 99.99% in about 4.1 years. The gamma factor at these velocities is approximately 1.005, 1.15, 2, 7.1, 22.4, 70.7. The ship time and external time diverge enormously at these high velocities. And the ratio, the gamma factor, grows as the velocity approaches the speed of light. To cross 100,000 light years in 12 years of ship time, the average gamma factor over the journey is approximately 8,333. This requires velocities extremely close to the speed of light, within fractions of a percent. The kinetic energy of a 1-ton spacecraft moving at gamma equals 8,333 is approximately 8,333 times the rest mass energy of that spacecraft. The rest mass energy of 1 ton is 9 times 10 joules. Multiply by 8,333 and you get approximately 7.5 times 10 squared, 0 joules. For comparison, the total energy output of the Sun in 1 second is about 3.8 times 10 squared, 6 joules. So, the kinetic energy of our 1-ton spacecraft at this speed is equivalent to approximately 2 milliseconds of the Sun's total energy output. That is not obviously an absurd amount of energy. The Sun is extraordinarily energetic, but for a civilization trying to propel not just a 1-ton probe, but a spacecraft massive enough to carry a crew, life support, fuel, and supplies, the energy requirements scale with the mass. A crewed ship might mass thousands of tons. The energy scales accordingly. You are talking about harnessing the equivalent of seconds to minutes of the Sun's total energy output to propel a single spacecraft. Sun. Can't. This is a Type 2 civilization's enterprise in Kardashev's classification, a civilization that has mastered the energy output of its entire star. But the energy problem is only part of the engineering challenge. Equally daunting is the problem of the interstellar medium itself. At high fractions of the speed of light, the spacecraft does not encounter a gentle vacuum. It encounters a headwind of protons and atomic nuclei, whose kinetic energy in the spacecraft's reference frame is enormous. At 99.9999% of the speed of light, each hydrogen atom in the spacecraft's path carries the kinetic energy of a well-aimed rifle bullet. Not because the hydrogen atoms are moving fast in the external frame, but because the spacecraft is moving so fast that in its reference frame, the hydrogen atoms are moving toward it at 99.9999% of the speed of light. The interstellar medium, at these velocities, is an intense radiation environment. The spacecraft's leading surface would be bombarded by particles equivalent to a continuous high-energy particle beam. A crew without shielding would receive a fatal radiation dose in minutes. Even with shielding, the mass and complexity of adequate radiation protection add enormously to the engineering challenge. There is also the problem of interstellar dust. The interstellar medium contains not just gas, but micron-sized and larger dust particles, silicate grains, carbon grains, ice-coated particles, at a density of roughly 1 grain per million cubic meters. At near light speed velocities, a single such grain carries the kinetic energy of several kilojoules, equivalent to a small explosive. The spacecraft's forward face would encounter these grains many thousands of times per second, and each impact at relativistic speeds is a micro-explosion. Over the 100,000 light-year journey, the cumulative effect would be devastating without some form of shielding or deflection. Several proposals have been made for relativistic shielding, a thick hydrogen ice shield that ablates slowly over the journey, providing both radiation shielding and protection against dust impacts. Maybe electromagnetic deflection systems that ionize and deflect charged interstellar particles, or a magnetic sail that creates a bubble of magnetic field around the spacecraft large enough to deflect incoming ions. None of these are currently buildable. All are physically plausible in principle. Then there is the problem of navigation. Crossing 100,000 light-years of a galaxy that is itself rotating, with stars orbiting the center at hundreds of kilometers per second, spiral-arms winding and unwinding over millions of years. The positions of all stars shifting continuously means that the destination you aim for at the start of the journey is not where the ship's target is when you arrive, 100,000 years of external time later. The spiral arm you are heading toward has moved. The stars in it have moved. Navigation across galactic scales, on geological timescales, requires predicting the positions of stellar systems hundreds of thousands of years in advance, accounting for the gravitational interactions of hundreds of billions of stars and the dark matter distribution that governs galactic undoubtedly. Love, fear, destroyed. The astronomical precision required is not impossible. We already track the three-dimensional positions and velocities of millions of stars with Gaia-level precision, enough to extrapolate forward by thousands of years. But extrapolating 100,000 years requires understanding galactic dynamics at a level of precision that exceeds our current models. And communications, the ability to maintain any contact between the spacecraft and its origin civilization, become increasingly impossible as the journey proceeds. A radio signal traveling at the speed of light from Earth reaches the spacecraft only as far as the spacecraft has traveled, after twice the journey time. But because the spacecraft is moving at near light speed, the signals are also Doppler shifted to essentially zero frequency by the time they arrive. Communication at relativistic speeds requires accounting for the relativistic Doppler effect, which at 99.99999% of the speed of light shifts the received frequency by a factor of roughly 707. A transmission sent at radio frequencies would arrive at the spacecraft as extremely high-energy gamma rays. One sent at gamma ray frequencies would arrive as radio waves. Mission planning and communication protocols would need to account for this at every step, using transmitters and receivers designed for the appropriate relativistic frequency shifts. These engineering obstacles are not insurmountable in principle. They are the kinds of problems that a civilization far more advanced than ours might solve, with sufficient time and resources and ingenuity. But they illustrate why the question, how long would it take to cross the Milky Way, does not have a simple answer, even once you have the propulsion figured out. The propulsion is the smallest part of the problem, in a sense, or rather, it is the most dramatic part, the part that drives the headline numbers, but the other parts are no less challenging, and in aggregate, maybe more so. Let us take a step back from the engineering and return to the physics, because there is a perspective that makes the journey feel different. Not easier, not shorter, but different in character. The universe does not set a speed limit of the speed of light because it's cruel or arbitrary. The speed limit emerges from the structure of space-time, from the Lorentz symmetry that governs the relationship between space and time. And built into the same structure that imposes this limit is the mechanism that partially compensates for it: time dilation. The universe tells you that you cannot cross 100,000 light-years in less than 100,000 years of external time. But it also tells you that if you move close enough to the speed of light, you can experience that journey in a much shorter, subjective time. The universe is not saying you cannot go to the other side of the galaxy. It is saying that if you go, 100,000 years will pass at home while you travel, and you can compress your experience of the journey to as short a time as your propulsion allows. You can cross the galaxy in 12 years of your own time. What you cannot do is also have 12 years pass at home while you do it. This asymmetry is the deep physics of the situation. It is what makes interstellar travel, and especially intergalactic travel, a fundamentally different kind of enterprise from any travel that has come before. Every explorer who has ever set out across an ocean knew that when they returned, approximately the same amount of time would have passed at home as during their journey. Columbus was gone for 7 months and returned to a Spain that was 7 months older. Magellan's crew circumnavigated the Earth in 3 years and returned to a world 3 years older. An astronaut returning from the International Space Station after 6 months finds Earth 6 months older, with a tiny correction, a fraction of a millisecond, due to the very small time dilation experienced in low Earth orbit. A relativistic traveller returning from the other side of the Milky Way, having spent 12 years on the journey each way, 24 years total ship time, returns to Earth to find it 200,000 years older. They step off the ship, having aged 24 years, into a world separated from everything they knew by a span of time greater than the entire history of our species. Their civilization, their language, their culture, their friends and family, all of it gone, replaced by something utterly unrecognizable, or nothing at all. The traveller's 24-year adventure is an irreversible one-way ticket through time, as surely as any travel through a wormhole or time machine in science fiction. They have moved forward in time by 200,000 years. They cannot go back. This is what the physicist calls the twin paradox, though it is not a paradox. The mathematics is unambiguous. If two twins start together and one travels at high speed while the other stays home, the travelling twin ages less. The travelling twin returns younger than the stay-at-home twin. The difference in age is determined by the gamma factor, integrated over the journey. For a galaxy-crossing journey, the difference is not minutes or hours or years. It is geological EFOPS. The travellers return as time travellers, stranded in the future, cut off from everything they knew. This is not merely a thought experiment. It is a real physical consequence of a real physical law, tested and confirmed in principle by every muon detector ever built. Muons, subatomic particles produced in the upper atmosphere by cosmic rays, have a half-life of 2.2 microseconds in their own rest frame. Moving at 99.7% of the speed of light, they should decay after travelling only about 600 meters before reaching the detector at sea level. But we detect them at sea level, 15 kilometers below where they are produced. They live long enough to reach us because time dilation extends their lifetime in the ground's reference frame by the Lorentz factor, roughly 13 at 99.7% of the speed of light. Their internal clock runs slow. Their lifetime, in the external frame, is 13 times longer than in their own frame. Relativistic time dilation is not a theoretical prediction awaiting confirmation. It is the mundane daily reality of muon physics, measured in cosmic ray experiments for decades. It is also the daily reality of GPS navigation. The satellites of the Global Positioning System orbit at about 20,200 kilometers altitude, moving at approximately 3.87 kilometers per second relative to the ground. At this speed, they experience time dilation of about 7 microseconds per day. That is, their clocks run slightly slow compared to clocks on the ground due to their motion. They also experience gravitational time dilation. Their clocks run slightly fast compared to those on the ground because they are higher in Earth's gravitational field, where space-time is less curved. The net effect is that GPS satellite clocks gain about 38 microseconds per day relative to ground clocks. If this effect were not corrected, if the satellite clocks were simply allowed to run at their natural rate without relativistic correction, GPS positioning errors would accumulate at about 10 kilometers per day. Your phone's map would be unusable within minutes. The engineers who designed GPS built in relativistic corrections, running the satellite clocks at a slightly different rate than ground clocks to compensate for this effect. Every time you navigate with a GPS device, you are relying on Einstein's theory of relativity, both special and general, to give you an accurate position. Relativistic effects are not just theoretically interesting, they are practically essential. Now take those effects, familiar from GPS satellites and muon detectors, and scale them up to the velocities required for a galaxy crossing, and you begin to feel the full weight of what time dilation means at these extremes. A GPS satellite experiences 38 microseconds of net time shift per day. A ship travelling at 99.9999% of the speed of light experiences time dilation of a factor of 707. Every second on that ship corresponds to 707 seconds in the external universe. Every year on that ship corresponds to 707 years outside. The comparison is not quantitative, it is qualitative. The GPS satellite is in the regime where relativistic effects are a small but important correction to Newtonian physics. The interstellar ship, at 99.9999% of the speed of light, is in the regime where relativistic effects are not a correction. They are the dominant feature of reality. What would it feel like, subjectively, to travel at such velocities? The travellers on the ship would feel no particular sensation from the time dilation itself. They would not feel time passing slowly. Time, from their perspective, would pass at its normal rate, 1 second per second, 1 year per year. They would age normally. They would grow hungry and sleep and have conversations and experience the passage of time in all the ways humans always have. The 12-year crossing of the Milky Way would feel like 12 years. They would be 12 years older at the end. They would remember all 12 years as continuous lived experience. What they would notice is the outside universe. Looking forward in the direction of travel, they would see the light of stars blue shifted dramatically towards shorter, higher energy wavelengths. Stars that emit visible light would appear in the ultraviolet or X-ray. Stars that are normally invisible in X-ray would blaze into visibility. The stars ahead would appear compressed into a small bright patch in front of the ship, concentrated by relativistic aberration, the effect that causes the apparent direction of light sources to shift toward the direction of motion as speed increases. At near light speed, almost all the stars in the universe would appear to be concentrated in a bright point directly ahead, a ring of light surrounding the vanishing point of the direction of travel. Looking backward, the opposite effect. Stars redshifted into the radio and microwave, the sky behind appearing dark, almost empty, the visible stars all concentrated in the forward direction. The interstellar medium, those hydrogen atoms that pose such a radiation hazard at near light speeds, would arrive at the ship from ahead at relativistic velocities. In the ship's reference frame, each hydrogen atom encountered is a high-energy particle moving at 99.9999% of the speed of light. The kinetic energy of such a particle is approximately 707 times its rest mass energy. The rest mass energy of a proton is about 938 million electron volts. At gamma equals 707, the incoming protons carry about 663 billion electron volts each. For reference, the Large Hadron Collider at CERN accelerates protons to about 6.5 trillion electron volts in its highest energy runs, so the interstellar medium, at this speed, delivers protons at about 10% of LHC energy. The interstellar medium becomes, in the ship's reference frame, a dense beam of cosmic ray equivalent particles, bathing the ship's hull in radiation that would rapidly destroy unshielded electronics and kill unprotected crew. The shielding required, either physical mass or electromagnetic deflection, is one of the most significant engineering constraints on relativistic travel. Every proposal for such a voyage must address it. And communications. Even if the traveller wanted to send a message home, to tell the civilization that launched them what they have found, what the approach to the galactic centre looks like, what stellar systems they have passed, any message sent at the speed of light would take thousands of years to arrive. A message sent after 1 year of ship time travels at light speed and arrives at Earth after the time that has elapsed in the external frame during that first year of ship time. At gamma equals 707, 1 year of ship time corresponds to 707 years of external time. So the message arrives 707 years after the journey began, from the perspective of anyone on Earth. And by the time it arrives, the ship is 707 light years away, and any response would take another 707 years to reach the ship, by which point the ship, still travelling at near light speed, is 1,414 light years away, and the response, sent 707 years ago, is 707 light years behind the ship and will never catch up. The communication is essentially one way. Earth can never receive a timely response to any communication, and the travellers receive all Earth's communications with enormous delay and redshift. Psychologically, this isolation would be total. Whatever the travellers see and experience, whatever discoveries they make in the 12 years of their journey, remains theirs alone until they arrive somewhere and can transmit their findings to a new audience, one that did not exist when they left. They carry humanity's curiosity across the galaxy, but they carry it in a bottle they cannot open until they reach the other shore. Now consider what all this means for the question of whether the Milky Way is crossable. The answer depends on what you value. If what you value is the continuous connection of a society or civilization, the ability to send settlers across the galaxy and maintain some cultural or informational continuity with their origin, then the answer is that it cannot be done without technology we do not have and may never have. The travellers arrive at their destination after 12 years of their time, but to send any message back about what they find, another 100,000 years elapses for the message to return. The civilization that sent them is gone. There is no connection. There is no exchange. There is only departure and arrival, separated by a chasm of time that no communication can bridge. Colonizing the galaxy in a meaningful sense, maintaining a galactic civilization with any kind of informational or cultural exchange, is not permitted by the speed of light, regardless of propulsion technology. If what you value is exploration, understanding what is on the other side of the galaxy, seeing other stellar systems, mapping the structure of our galactic home, then the answer is more nuanced. Sending robotic probes at high fractions of the speed of light to explore nearby stellar systems is the first step, and it is, at least in principle, within the reach of a civilization a few centuries or millennia more advanced than ours. Sending humans is a much larger challenge, but not a physically impossible one. Multi-generational ships, spacecraft large and self-sufficient enough that multiple generations live and die on board during the journey, with descendants arriving at the destination long after the original crew has died, are one solution for non-relativistic speeds. At 10% of the speed of light, the Milky Way crossing takes 1 million years, and a multi-generational ship becomes a generational civilization rather than a vessel. At 99% of the speed of light, the journey takes a century of ship time, conceivable, though barely, for a single long-lived generation in a purpose-built ship. Save and create a time for save, and another species among low sides will be the final weekends of the save.
If what you value is the raw challenge, the physics question, the what is the minimum ship time under the best plausible physics, then the answer, for continuous 1G acceleration, is approximately 12 years for the crossing, or around 24 years round trip, with 200,000 years elapsed at home. With higher acceleration, the ship time shrinks further. At 10 grams, the crossing is achieved in roughly 2.5 years of ship time. At 100 grams, brutally lethal for an unprotected human, but survivable in theory with the right life support engineering, it drops to less than a year. The physics does not forbid the journey. It enforces a trade. Your ship time decreases, but the time dilation means you are always planting yourself ever further into the future of your civilization. Every acceleration you use to shorten your journey makes you more of a time traveler.
There is no escaping this trade. It is written into the structure of space-time. Now let us zoom out and consider the Milky Way crossing in the context of what we know about the galaxy structure, because the journey through the galaxy is not through a uniform medium. It is through a complex and varied environment that would itself be one of the most extraordinary experiences imaginable, whether you lived through it on a 12-year ship time or contemplated it from afar. The journey begins, let us say, from Earth's position in the Orion Arm, heading toward the galactic center and beyond to the far edge. In the first 26,000 light years, the ship passes through the disk of the galaxy, through increasing stellar density as it approaches the galactic bulge. The number of stars per cubic parsec in the galactic neighborhood of the Sun is roughly 0.14. In the inner bulge, this rises to hundreds per cubic parsec. The night sky from a ship in the inner bulge would be blazing with light. Thousands of stars brighter than Venus appears from Earth. The sky never truly dark. The galactic center, a brilliant concentration of light, bright enough to cast shadows on the ship's hull. At the center of the galaxy, Sagittarius A awaits, the supermassive black hole at the Milky Way's heart, with a mass of 4.15 million solar masses, surrounded by a dense cluster of young, hot, massive stars and a disk of ionized gas swirling around the event horizon at significant fractions of the speed of light. The S2 star, one of the best studied objects in this region, orbits Sagittarius A star with a period of just 16 years and achieves a closest approach velocity of about 7,650 kilometers per second, 2.5% of the speed of light. This is the fastest moving star we have ever directly observed. If our spacecraft had to navigate the inner parsec of the galactic center, it would do so in an environment where stars are moving at percentages of the speed of light on their own orbits, where tidal forces from the black hole are significant, where gamma-ray emission from infalling matter and annihilating cosmic rays bathes everything in high-energy radiation. Passing through the center and continuing toward the far edge of the galaxy, the stellar density drops back as the ship moves through the far spiral arms and eventually into the outer disk, where stars become sparse, metal-poor, and isolated. The galactic frontier, where heavy elements are rare because there have been fewer generations of stars to produce them. The gas density in the outer disk drops. The interstellar medium thins. The journey ends somewhere in the outer reaches of the galactic disk, 100,000 light-years from where it began, in a region of space that, from Earth, is visible only as a faint smear of light in the constellation Auriga or Perseus, depending on direction. What the travellers would find there, what stellar systems exist on the far side of the galaxy, what planets, what conditions, what possibilities, is almost entirely unknown. We have no detailed observations of the stars on the far side of the galactic centre. The galactic centre itself is opaque at optical wavelengths, obscured by dust and gas, visible to us only in radio, infrared, and X-ray. The far side of the galaxy is effectively terra incognita. We know its stars are there because the galaxy's rotation curve tells us about its total mass distribution. We know something about its spiral structure from radio observations of hydrogen emission, but the individual stellar systems, the potential planets, the possibilities, these are unknown to a degree that the far side of the Earth's oceans was unknown to medieval Europe, and then some. This is one of the most striking things about the question we have been asking. The Milky Way is our home. We have lived in it for the entirety of our species' existence, and the entirety of Earth's history, and the entirety of the Sun's history. It is not some distant other galaxy, it is the structure that contains us. And yet it is so vast, and the speed of light so limiting, that we have not been able to observe most of it in any detail. The far side of our own galaxy is more mysterious to us than the surface of Mars. We have spacecraft on Mars. We have seen its rocks and its dust and its ancient river channels in centimetre-scale detail. The far side of the Milky Way, 30 times closer than the nearest other large galaxy, is beyond our direct, detailed observation. We cannot see through the galactic centre to the stars on the other side. Radio waves at 21 centimetres, the wavelength emitted by neutral hydrogen atoms, can penetrate the galactic dust and reveal the structure of the far side's spiral arms. Gaia, the European Space Agency's astrometry satellite that has mapped the positions and motions of nearly 2 billion stars with extraordinary precision, has extended our knowledge of the Milky Way's structure significantly. The Vera Rubin Observatory, JWST, and future missions will continue extending that map. But the full census of the Milky Way, every star, every planet, every stellar system, is not achievable from Earth, and the only way to truly know what is on the far side of the galaxy is to go there. Which brings us back to the fundamental tension at the heart of this question. The Milky Way is ours. It is our galaxy, our cosmic home, the structure whose gravitational field has shaped our planet's history, whose supernovae have seeded our solar system with heavy elements, whose dark matter halo holds us in orbit around a gravitational structure 100 times larger than we can see, and we cannot leave it on any human timescale with any technology we are anywhere near building. The nearest star, Proxima Centauri, at 4.24 light-years, is a 73,000-year journey for Voyager 1. The galaxy is 24,000 times farther than that. nearest star, we are, in any realistic sense, anchored here, not by choice, not by lack of imagination or ambition, by the structure of the universe, by the speed of light and the distances it implies, by the Wackett equation and the energy densities of available fuels. This anchoring is one of the deepest facts about our situation. We are not near the edge of any exploration frontier in the way that Magellan was, or Columbus, or even the Apollo astronauts. We are not one generation of better ships away from crossing the galaxy. We are separated from any realistic crossing of even a fraction of our galaxy's extent by technological gaps so large that they are better measured in types of civilization, in Kardashev levels, than in generations of engineers. A Kardashev Type 2 civilization, commanding the full energy output of its star, might manage a fast probe to a nearby stellar system. A Kardashev Type 3 civilization, commanding the energy output of its entire galaxy, might manage relativistic travel across significant galactic distances. We are a Type 0.7 civilization, commanding roughly 10 squared watts of total power use, still dependent on chemical rockets for much of our space travel, still struggling to sustain controlled nuclear fusion, still decades from any working fusion power plant. It is worth pausing here to consider the alternative proposals for making the crossing survivable without relativistic speed, because the answer to how long does it take is not only lie in making the vehicle faster, it also lies in making the travellers different, in changing not the physics of propulsion, but the biology and psychology and sociology of the crew. The most frequently discussed of these alternatives is the generation ship, a spacecraft so large and self-sufficient, but it functions as a closed ecological and social system capable of sustaining a human population through the entire journey. With multiple generations born, living and dying on board before the destination is reached. At 10% of the speed of light, the kind of velocity fusion propulsion might achieve, the Milky Way crossing takes 1 million years. That is roughly 40,000 human generations, assuming a generation length of 25 years. The social and cultural implications are staggering. After 40,000 generations in an enclosed, isolated environment, the descendants of the original crew would bear roughly the same genetic and cultural relationship to them as we do to the Homo erectus populations who were making stone tools in East Africa 1 million years ago. The concept of a destination, of a place the ship was launched toward, a goal the original crew had, would have become mythology, then legend, then perhaps entirely forgotten long before arrival. The ship would not be a vehicle crossing the galaxy. It would be a world in itself, with its own history, its own evolution, its own forgotten origins. Generation ships at subrelativistic speeds are therefore not a practical solution to galactic colonization. They are a thought experiment about the creation of new civilizations, not the extension of existing ones. The descendants who arrive are not the civilization that launched. They're something new, something that grew in the vessel, that knows the journey as their world and the destination as a myth told for generations beyond counting. A more technologically imaginative solution is suspended animation or cryogenic preservation, placing the crew in a state of biological stasis during the journey so that they experience little or no time passing, and arrive at the destination having aged only the hours or days required to enter and exit the suspended state. No time dilation needed, no generation ship, no multi-generational odyssey, just sleep and then arrival. This concept has deep roots in science fiction, and it is taken seriously enough that several companies and research programs are investigating biological stasis for medical and spaceflight applications. SpaceWorks Enterprises proposed a concept called torpor-induced migration, which involves inducing a mild, controlled form of therapeutic hypothermia, cooling the body to about 32 degrees Celsius, slowing the metabolism dramatically in astronauts for weeks at a time. The concept could, in principle, be extended to longer durations with more research into the biology of long-duration metabolic suppression. The challenge is that the biology of mammalian suspended animation is not well understood. Some mammals hibernate naturally: bears, ground squirrels, certain bats. But true hibernation involves metabolic rates only a few % of normal, not the near zero rates that would be needed for a journey of decades or centuries. The neural and cellular damage that accumulates during prolonged cooling, the difficulty of controlled rewarming, the effects on the immune system, the long-term consequences for cognition and personality, none of these are solved problems. And even if biological stasis were perfected, it solves only the subjective experience of the journey, not the objective distance. At Voyager's speed, the 1.75 billion year crossing would require stasis, not for a century, but for geological epochs, longer than complex life has existed on Earth. No biology survives a billion years of cosmic ray bombardment, even in stasis. At more ambitious speeds, 10% of the speed of light for a million-year crossing, the stasis problem becomes: can you preserve a human body in perfect biological suspension for a million years? The answer is almost certainly no, unless preservation means something more like the digital archiving of the mind's information pattern and its reconstruction at the destination, which is a completely different concept, requiring a completely different set of technologies and raising completely different philosophical questions about personal identity and consciousness. The digital mind option, sometimes called mind uploading or whole brain emulation, would, if feasible, trivialize the travel problem in a particular sense. A digital representation of a human mind could be transmitted at the speed of light, arriving at the destination 100,000 years after transmission, where it could, in principle, be reconstructed in a new physical substrate. The transmission itself would take 100,000 years, and the traveller would experience no subjective time. The transmission is not a stream of consciousness, but a static description of a mind state, which is then reconstructed. Another reconstruction is the same person as the original, or merely an identical copy, is a philosophical question that the physics does not resolve. And the infrastructure required at the destination, facilities capable of reconstructing a digital human mind in a physical body, must be built and maintained for 100,000 years before the signal arrives, requiring either preceded robotic infrastructure or an existing civilization at the destination to prepare. None of these alternatives, generation ships, stasis, digital transmission, solves the problem in a way that preserves anything recognizable as a continuous human civilization crossing the Milky Way. They each transform the crossing into something different: a founding myth, a biological experiment, a philosophical puzzle about identity. The crossing, if it happens, will not be a journey. It will be a transformation. There is one more timescale worth mentioning, not as a propulsion option, but as a cosmic reminder of how the galaxy itself changes on these vast timescales: the Andromeda collision. The Andromeda galaxy, Messier 31, the nearest large galaxy to the Milky Way, at approximately 2.5 million light-years, is approaching us at roughly 110 kilometers per second, with a significant transverse velocity component as well. Detailed measurements from the Hubble Space Telescope, and subsequently from Gaia, have established that the two galaxies will begin a close gravitational interaction in approximately 4.5 billion years, eventually merging into a single elliptical galaxy, roughly 8 to 10 billion years from now, a configuration astronomers have nicknamed Milky Way. During this merger, the stellar density of the combined system will change dramatically. Some stellar systems will be ejected into intergalactic space, and the beautiful spiral structure of both galaxies will be destroyed, replaced by the smoother, elliptical profile of the merged system. This is relevant to our travel question in a specific way. The Milky Way we know today, with its 100,000 light-year disk, its two major spiral arms, its relatively ordered orbital structure, will not exist forever. It will exist for approximately 4.5 billion more years, and then begin to be disrupted by the Andromeda encounter. Any civilization that hopes to cross the Milky Way, as it currently exists, from this spiral arm to that one, through the galactic center, out the other side, must do so before the merger disrupts the structure. 4.5 billion years is an enormous span of time, enough for entire new chapters of biological evolution on Earth, enough for the Sun itself to exhaust its hydrogen fuel and expand into a red giant. But it is not infinite. The galaxy is a temporary configuration. Everything is temporary on a long enough timescale. And this, finally, is what the question of crossing the Milky Way is really about. Not speed, not propulsion, not time dilation, though all of these are part of it. It is about the relationship between the timescales of human life and human civilization, and the timescales of the cosmos. We live for decades. Our civilizations persist for thousands of years, if we are lucky. Our species has existed for a few 100,000 years. And the Milky Way is 100,000 light years across and 13.5 billion years old, rotating on a timescale of hundreds of millions of years, destined to collide with another galaxy in 4.5 billion years, eventually to settle into a new configuration that no one now living will recognize. The crossing of the Milky Way is, in a real sense, not a problem we will solve. It is a measure of where we are, of the vast, humbling distance between what we are and what we would need to be to make such a journey, and of the equally vast, equally humbling distance between the life of a human being and the life of a galaxy. We are not going to cross the Milky Way. Not soon, perhaps not ever. But we know its size, its structure, the speed needed, the time required, the physics that governs the journey, the cost in time and isolation, and irreversible future-directed travel that any crossing imposes. We know all of this from here, from this particular location in the Orion arm of a barred spiral galaxy, 26,000 light-years from the center, using instruments made of the same atoms that the galaxy produced in stellar interiors over billions of years of nuclear burning. And yet, the fact that we cannot currently cross the Milky Way does not mean we cannot understand it. And understanding the Milky Way, knowing its structure, its history, the nature of its stars and stellar remnants and black holes and dark matter halo, the distribution of potentially habitable planets within it, the timeline of its merger with Andromeda in 4 billion years is itself a profound achievement. Knowing the answer to how long would it take is itself knowledge of a kind, because it tells us what kind of universe we live in and what kind of civilization we would need to become. The distance to the far side of the galaxy is, let's find, a series of politics by no one who lives all the life in the new civilization. It is a measurement that tells us how large our home is, how much it contains, how much there is to know within it. Consider what has happened in the last 100 years of astronomical observation. A century ago, the Milky Way was thought to be the entire universe. Edwin Hubble had not yet resolved the distance to the Andromeda Nebula. The cosmic microwave background was unknown. Dark matter was undetected. The supermassive black hole at the galactic center was unsuspected. The structure of the spiral arms was unmapped. Even the location of the Sun within the galaxy was uncertain. Harlow Shapley's measurement of the distances to globular clusters in 1918, which placed the galactic center in the direction of Sagittarius, was the first solid evidence that the Sun was not at the center of the Milky Way. Before Shapley, it was entirely reasonable to believe we lived near the center of whatever the universe was, that the Milky Way was roughly symmetrical around our position, a galaxy whose heart was approximately where we stood. Shapley's measurement, based on the distribution of globular clusters across the sky and their calculated distances, showed that the true center of the Milky Way was not near Earth, but roughly 26,000 light-years away in the direction of Sagittarius, and that the Milky Way was far larger than previously estimated. End of section 7. We moved from center to periphery in a single observational campaign. We have never returned to center. Every subsequent measurement has confirmed that the Sun sits in the disk of the galaxy, a substantial but not extreme distance from the center, in a quiet spur between spiral arms, neither special nor particularly notable in the galactic geography. In 100 years, we went from not knowing the size of our galaxy or our position within it, to mapping nearly 2 billion of its stars with Gaia-level precision, measuring the mass distribution of its dark matter halo through stellar kinematics, imaging the accretion disk of its central black hole in radio wavelengths with the Event Horizon Telescope in 2022, detecting gravitational waves from stellar mass black hole mergers throughout the galaxy with LIGO and Virgo, and building models of its formation and evolution from the first galaxies through the present day. We cannot travel across the Milky Way. But in a century, we have gone from not knowing its size to mapping it in extraordinary detail from a fixed point, using light and radio waves and gravitational waves as our instruments. The history of how we measured the galaxy is itself extraordinary, and it is worth dwelling on for a moment, because it is a testament to human ingenuity in the face of the same impassable distances we have been discussing all through this video. The first rough measurements of the galaxy's size came from counts of stars in different directions, pioneered by William Herschel in the late 18th century. Herschel counted stars in 683 different regions of the sky and found that the counts were greater in the plane of the Milky Way and smaller perpendicular to it, leading him to the conclusion that we live in a disc-shaped system. He estimated the disk to be about 5 times wider than it was thick, a correct qualitative conclusion, but badly underestimated its actual size because he could not see through the dust in the galactic plane, which absorbs visible light and makes distant stars invisible. He placed the Sun near the center of his estimated disk. The dust that hid the true extent and center of the galaxy would confound observers for more than a century. The breakthrough came with a change of wavelength. In the 1950s and 1960s, radio astronomers discovered that the hydrogen atoms in the interstellar medium emit radio waves at a wavelength of 21 centimeters when the electron in a hydrogen atom flips its spin. Radio waves at 21 centimeters pass through the interstellar dust with almost no absorption, penetrating the galaxy to distances completely inaccessible at optical wavelengths. By mapping the 21 centimeter emission across the entire sky and measuring the Doppler shifts of the emission, which reveal the velocities of the emitting hydrogen clouds, and thus their distances. Using the known rotation curve of the galaxy, radio astronomers were able to trace the structure of the Milky Way spiral arms across the full disk, including regions on the far side of the galactic center that optical astronomers had never been able to see. The radio maps revealed a spiral structure that had been invisible to optical astronomy for centuries. The next revolution came from infrared. Infrared radiation, like radio waves, is less affected by interstellar dust than visible light, allowing infrared telescopes to penetrate much deeper into the galactic disk and center than optical instruments. The IRAS satellite in 1983, the 2MASS All-Sky Survey in the early 1900s, and the Spitzer Space Telescope from 2003 onward produced infrared maps of the Milky Way that revealed the galactic bar, the elongated central structure from which the spiral arms emerge, with a clarity impossible at optical wavelengths. The bar is tilted at roughly 27 degrees to our line of sight to the galactic center, a detail that matters for understanding the galaxy's rotation in spiral arm structure. And then Gaia, the European Space Agency's astrometry mission, launched in 2013, transformed our knowledge of the Milky Way in ways that previous instruments could not have enabled. By measuring the positions, parallaxes, and proper motions of nearly 2 billion stars with micro-arcosecond precision equivalent to measuring the thickness of a human hair from 3,000 kilometers away, Gaia produced the most detailed three-dimensional map of the Milky Way ever assembled. From Gaia's data, astronomers have discovered that the galactic disk is not flat, but warped. It bends upward on one side and downward on the other, like a cosmic vinyl record left in the sun. The warp extending to the outer disk thousands of light years above and below the central plane. They have discovered streams of stars, the debris of ancient globular clusters and dwarf galaxies that were disrupted by the Milky Way's gravity and scattered into long, thin arcs of stars orbiting the galaxy that trace the history of the Milky Way's cannibalism of its smaller neighbours over billions of years. They have measured the three-dimensional velocity of stars throughout the disk and found structures that were completely invisible in previous surveys: phase space spirals, velocity streams, disk oscillations that reveal the galaxy is not in a simple equilibrium, but is still ringing from the gravitational perturbation of a satellite galaxy that passed through the outer disk a few billion years ago. The Milky Way, in other words, is not a static, settled structure. It is a dynamic, evolving, still disturbed system, a galaxy that has been merging with smaller companions throughout its history, that will merge with Andromeda in the future, that contains within its stellar populations the fossil record of all those past mergers. Every stream of stars from a disrupted dwarf galaxy is a chapter of the Milky Way's history, written in stellar dynamics. Reading those chapters is one of the great scientific programs of the current era, and Gaia is making it possible for the first time. The next generation of instruments will push further still. The Square Kilometre Array will map the 21 centimetre hydrogen emission across the full sky with sensitivity and angular resolution far exceeding anything previously achieved, revealing the spiral structure of the far disk and the kinematics of the outer galaxy in unprecedented detail. The Nancy Grace Roman Space Telescope will survey the galactic bulge, detecting billions of stars in the near-infrared and searching for microlensing events, the temporary brightening of a background star when a foreground compact object crosses the line of sight, that reveal the masses and positions of stellar fire, remnants, black holes, and free-floating planets throughout the inner galaxy. A proposed extreme large telescope in space or ground-based extremely large telescopes like the ELT under construction in Chile will resolve individual stars in environments too crowded and distant for current instruments. We are in the middle of a golden age of galactic cartography. Every decade brings new instruments, new techniques, new discoveries that revise and deepen our picture of the Milky Way. The galaxy that was an unmapped mystery a century ago is becoming, incrementally, a known place. Not known in every detail, not mapped to every star, not understood in every process, but increasingly characterized, increasingly legible, increasingly familiar in the way that a landscape becomes familiar, not when you have walked every inch of it, but when you have studied its topology from enough angles that you understand its shape. And understanding its shape, knowing how large it is, where we are within it, what structures it contains, how it formed, and how it will evolve, is itself a profound achievement. One that took the entire history of astronomical observation to reach. One that continues to deepen with each new mission, each new survey, each new generation of astronomers asking the questions their predecessors could not yet answer. The next century will bring more. The Square Kilometre Array, a radio telescope currently under construction in South Africa and Australia, with an effective collecting area of 1 square kilometre, will map hydrogen emission across the galaxy with unprecedented sensitivity, revealing the spiral structure of the far side and the kinematics of the interstellar medium in the outer disk. The Nancy Grace Roman Space Telescope, with its wide-field infrared camera, will survey the galactic bulge and detect billions of stars that are invisible at optical wavelengths due to dust absorption. JWST continues to probe stellar populations and interstellar chemistry across the galaxy. Future astrometry missions may extend Gaia's reach to billions more stars, building a complete kinematic map of the Milky Way. We will not cross the galaxy in our lifetimes, or in our civilization's current form, but we will know it with increasing depth and completeness from right here. 100,000 light years of space between the near edge and the far edge will be mapped, modelled, understood, not by travellers who have crossed it, but by observers who have spent centuries examining it with every instrument that physics permits. And that is its own kind of journey. Not a physical one, not a journey through space, a journey through understanding. A journey that has been going on since the first human looked up and noticed that the sky was not uniform, that there was a band of light arching overhead, that the night was not just darkness, but structure, and wondered, for the first time, what that structure was. But there is a question that cannot be avoided once you have spent time thinking carefully about the distances involved, about the timescales, about what is physically possible with advanced propulsion and what is not. It is a question that the physicist Enrico Fermi reportedly asked at a lunch conversation in 1950, in a formulation simple enough to fit on a napkin. If the galaxy is crossable, even with extreme difficulty, even over geological timescales, where is everybody? This is the Fermi paradox, and it is directly and inextricably connected to the question of galactic travel. Here is the logic. The Milky Way is approximately 13.5 billion years old. The oldest stars in the galaxy formed within the first billion years of the universe's existence. The Sun is 4.6 billion years old. It formed more than halfway through the galaxy's history. If life arose on Earth in the first billion years after the Sun formed, then other stars that are only slightly older than the Sun, say, a billion years older, had a billion extra years for life to develop, and for any resulting civilizations to mature. A civilization only 1 million years more advanced than ours, a blink of a geological eye, given the 13.5 billion year age of the galaxy, would have had time to colonize the entire galaxy, even at sublight speed velocities,
using multi-generational ships or von Neumann probes.
A von Neumann probe is a self-replicating spacecraft, a machine that arrives at a stellar system, uses the local resources to build copies of itself, and sends those copies to neighbouring stars, which do the same, and so on. The replication is exponential. Even if each probe travels at only 1% of the speed of light and takes 100 years to replicate at each system, the galaxy can be colonized in roughly 10 million years. The entire process of colonization from launch to completion taking 1,000th of the age of the galaxy. Any civilization that launched such probes, even 5 million years ago, would have probes in every stellar system in the Milky Way by now. And yet, as far as we can tell, there are no such probes here. There are no alien artifacts in our solar system. There are no signals from a spacefaring civilization colonizing the galaxy. There is silence. The silence is deafening, and it connects directly to our travel calculations. If the galaxy is colonizable, if physics permits transversal, even slowly, even at vast cost, then the expectation is that the galaxy should be full of civilizations, or of the artifacts and traces of civilizations. The Great Silence, as the Fermi paradox is sometimes called, suggests one of several unsettling conclusions. Either intelligent life is extraordinarily rare, so rare that we are perhaps the only civilization in the galaxy, despite the billions of potentially habitable planets, or civilizations inevitably destroy themselves before achieving galactic colonization, or the physics of colonization is harder than the simple calculations suggest, or colonizing civilizations are choosing not to colonize in ways that remain invisible to us, or our assumptions about what colonization would look like are wrong. Each of these possibilities has been explored at length by researchers in the field, now called SETI, the search for extraterrestrial intelligence, and by theorists working on what is sometimes called astrobiology, or the study of the prevalence of time. Life in the universe. None of the proposed resolutions is clearly correct. The Great Filter Hypothesis, the idea that there is some critical bottleneck in the development of civilizations, a filter through which most intelligent species fail to pass, is one of the most discussed frameworks. If the filter is in our past, if the origin of life, or the origin of eukaryotic cells, or the origin of multicellular life, or the development of intelligence itself is so improbable that it occurs almost never, then we may be genuinely alone, or nearly so, in the galaxy. If the filter is in our future, if the natural endpoint of technological development involves self-destruction through nuclear weapons, engineered pandemics, artificial intelligence, or some other catastrophic that awaits any civilization that reaches our level, then the silence is a warning. The connection to our travel calculations is this: the physics permits the galaxy to be colonized on timescales of millions to tens of millions of years, even without relativistic propulsion. The fact that it apparently has not been colonized, that we see no evidence of other civilizations, no megastructures, no Dyson spheres, no directed communications, no artifacts, is a puzzle whose solution bears directly on what we should believe about the distribution of life and intelligence in the galaxy. If we are alone, then the 100,000 light-year crossing of the Milky Way is a journey we could, in principle, undertake and be certain of being the first. If we are not alone, if there are other civilizations in the galaxy that have solved propulsion problems we have not yet imagined, then the silence of the galaxy is itself a profound mystery, and the question of crossing it is shadowed by the question of who else is out there and why they have not announced themselves. There is a separate and more intimate connection to the travel question, which is the issue of what a civilization that can cross the galaxy actually looks like, and whether it is recognizable as a civilization in any sense we would understand. A civilization that has been expanding through the galaxy for 1 million years, seeding stellar systems with colonies, sending probes ahead to the next stars, evolving culturally over spans of time that dwarf the entirety of human history, would be so different from us that the word civilization barely applies. The colony on the far side of the galaxy, founded 100,000 years after the original launch, descended from the original civilization through thousands of generations of cultural and biological evolution in an isolated environment, would not be the same civilization. It would be something new, something we could not predict or recognize from our vantage point. The Milky Way, if it is or were ever to be colonized, would be not a single galactic civilization, but a vast diaspora of radically diverged cultures, each adapted to its local stellar environment, each isolated from the others by the light-speed barrier, each evolving on its own trajectory over geological timescales. This is the deepest implication of the travel calculations we have been doing all through this video. Not just that the crossing is hard, or that it takes a long time, but that the physics of the situation, the finite speed of light, the time dilation that separates travelers from their origin, the impossibility of maintaining real-time communication across galactic distances, means that a galactic civilization is not just a scaled-up version of a terrestrial civilization. It is something categorically different. It cannot have a unified government, a shared culture, a common language, a collective identity in any meaningful sense, because no information can travel fast enough to maintain those things across 100,000 light years. A galactic civilization is, by physical necessity, a galaxy of separate civilizations, sharing only the physics that governs them all, and the distant biological ancestry that connected them at the beginning. This is humbling, and it is clarifying. It tells us that the question of crossing the Milky Way is not just an engineering challenge or a physics puzzle. It is a philosophical confrontation with what we are, what we value, and what we are willing to become. To cross the galaxy is to become something different from what you were when you left. The time dilation ensures it, the distance ensures it, the isolation ensures it. You leave as a human being, embedded in a civilization, connected to a history, aware of your place in a chain of culture and memory stretching back through your parents and their parents, and all the generations before them. You arrive as something that has no such connection, because the chain has been severed, not by death, but by time. By 100,000 years of time flowing past while you travelled. The answer, it turns out, is that the structure is everything. It is 100 billion stars and 10 times as many planets, and ancient globular clusters and stellar nurseries, and supernova remnants, and a supermassive black hole at the centre, pulling everything around it in a stately orbit of 250 million years. It is the place where the atoms in your body reforged, in the interiors of stars that lived and died before the sun existed. It is the place that contains every civilization, if there are others, that shares our cosmic address. It is, in the most literal sense, home. And crossing it, really crossing it, physically, propelling a vessel from one edge to the other, would take, at the speed of light, 100,000 years. At the speed of Voyager, 1.75 billion years. At the speed of a fusion-powered spacecraft, hundreds of thousands of years. And at the best relativistic physics permits, and a continuous 1g acceleration, 12 years of your own experienced time, while 100,000 years of external time flows past you like a river. Not a fast river, the slowest river that has ever existed, the river of geological epochs, the river in which mountains are born and erode and are born again. You would arrive on the far side of your galaxy, 12 years older in your bones and your memories, having departed from a civilization that is now 100,000 years in the past. Not history, not archaeology, not even written record. Before the earliest cave paintings in Lascaux, before the last ice age, before the extinction of the Neanderthals. You would be cut off from everything you knew by a chasm of time greater than the span separating us from the first members of our species. And the galaxy would still be there, turning slowly, one arm reaching across the dark, its 100 billion stars burning with their patient, ancient fire, indifferent to the crossing, indifferent to the arrival, indifferent to the fragile, brief, extraordinary thing that made the journey and arrived and looked around and thought, we did it. We crossed the Milky Way. Whether that fragile, brief, extraordinary thing could bear the weight of what it found, a universe 100,000 years older, its home civilization vanished, its language forgotten, its name unknown to any living being, is a question not of physics, but of the human spirit. Physics tells you the cost. Only something beyond physics tells you whether it is worth paying. The universe does not close the door. It charges an admission price that is measured in time itself. How much time are you willing to spend? How much future are you willing to enter, never to return from? That is the question. That is always the question. Not how fast can we go, but how much are we willing to give, and what are we willing to become in the crossing?